Hello and welcome to the lecture on 10.8. Today we're going to talk about the systems of nonlinear equations. So this section is actually going to be much like the previous sections, except instead of using a system of linear equations, we're now using nonlinear equations. Let's recall really quickly. A linear equation has the form ax plus by equals c. So in this section, we're going to be looking at stuff that has equations that don't look like this necessarily. Maybe they don't have a power 1, maybe they have a power 2, maybe they have a power 3, maybe they have a square root. There's many different types of equations that we can use other than linear equations, and that's what we're going to try to solve in this section. But all of the techniques are the same. So let's start with substitution and elimination. Start out with an example here. Solve the system. X squared plus y is equal to 9. X minus y is equal to -3. Now this is a system of nonlinear equations because we have an x squared. Granted, this is a linear equation, sure, but the system isn't composed of exclusively linear equations. We have one linear equation, but we also have a nonlinear equation. Therefore, the system is nonlinear. Now, I'm going to use substitution in this problem. And what I want to do first is I want to solve for y here. Basically, what we're looking for here is any ordered pair that satisfies both of these equations, just like before, except before we had linear. Now we have nonlinear equations. So what we're looking to find are all of the ordered pairs that satisfy both of these equations. And it's not going to necessarily be one, and it's not going to necessarily be infinitely many. We can have a fixed number because we have a system of nonlinear equations. And we'll get to that in a bit. When we get to the graphical method, I'll show you exactly what I mean. So here what I'm going to do is I'm going to solve for y first in this equation. Call this one equation 1, this one equation 2. And if we solve for y in equation 2, we end up with y is equal to x plus 3. We add our 3, add our y, we have y equals x plus 3. Now, I'm going to substitute equation 2 into equation 1 for y. Now, I do this because I want to keep my x squared here. Because an x squared, a quadratic equation, has the potential of having more than one value as a solution. So we look at equation 1 and we say 1 such that y is equal to x plus 3. That will give us x squared plus x plus 3 equals 9. Then we would solve this quadratic equation just like we would solve any quadratic equation in chapter 2. Set it equal to 0 by subtracting 9. We have x squared plus x minus 6 is equal to 0. And then we factor. And here we're looking for two numbers that multiply to -6 and add to +1. That's going to be 3 and 2. Specifically 3 and -2. So this factors into x plus 3 times x minus 2 is equal to 0. And we can go straight to the end again because we have a 1 as a leading coefficient here. So then we have x is equal to 2 and x is equal to -3. Now we need to pause for a second because we haven't had this before when we're solving a system of equations. We haven't had two different x values that are solutions. We have one x, one y, one z, or we have infinitely many solutions where we set one variable equal to t, and then we solve all of the other variables in terms of t. But here we've never had where x could be 2 and x could be -3. Well, this is actually not uncommon. If you think about what these nonlinear equations look like, for instance, this one is a parabola, and this one is a line. And when we get to the graphical representation, you'll see that the line can actually intersect a parabola in multiple places. Since it can intersect in multiple places, we can have multiple solutions. And this happens to be one of those cases. So we said y is equal to x plus 3. So now I'm going to go back to equation 2, such that x is equal to 2, where 2 is equal to y equals x plus 3, so we would have y is equal to 2 plus 3. Now, note here, in this equation, I'm saying that x is equal to 2. I already have my x solved for. So we end up with y is equal to 5. So when x is 2, y is 5. So we have the point 2, 5. No other points come out of this equation, just 5. When x is equal to negative 3, and we look at equation 2, such that x is equal to negative 3, we get y is equal to negative 3 plus 3. In this case, we get y is equal to 0. Again, when x is equal to negative 3, y is equal to 0. So we get the point negative 3, 0. These are my two solutions to this system, and we can check it if we want to. Plug in 2 for the equation 1. That's 4 plus, plug in 5. We have 4 plus 5 is 9. Plug 2, 5 into the second. 2 minus 5 is negative 3. And then plug negative 3, 0 into the first equation. Negative 3 squared is 9, plus 0 is 9. Then negative 3 minus 0 is negative 3. So both of these points satisfy the system of equations. Therefore, they are both solutions to our system. Note that we do not have infinitely many, nor do we have a single solution. It's possible to have any number of solutions, not just the 3 cases that we had before, where you had one solution, infinitely many solutions, or 0 solutions. And we can see that, obviously, because we have 2 solutions here. I cannot emphasize enough how we find the values, though. When x is equal to 2, we get y is equal to 5. And when x is equal to negative 3, we get y is equal to 0, right? I recommend that you do these type of bookkeeping steps in order to highlight what your points will actually be at the end, because it can get confusing. Try one on the accompanying worksheet. Use substitution to solve the system. X squared plus y squared is equal to 8, and x plus y is equal to 0. Let's jump into the elimination method now. Example. Solve the system. X squared plus y squared is equal to 9. X squared minus y squared is equal to 1. Call this equation 1, call this equation 2. Now we could do substitution, and substitution actually wouldn't be too bad here. So you can solve for x squared or y squared in one equation and then plug it into the other. You do not want to solve for y and x. You want to solve for x squared or y squared because we have an x squared and y squared everywhere. There is no x, there is no y, just x squareds and y squareds. So you would want to solve for x squared and y squared to save yourself some time. I'm going to use elimination though, and do equation 1 plus equation 2. Just like before, the elimination method is identical to how we did it when we had a system of linear equations. It's just now we have nonlinear equations, so it's possible to get multiple solutions. So if we add these two together, we get x squared plus x squared. That's 2x squared. Y squared minus y squared is 0, and 9 plus 1 is 10. So we then get x squared is equal to 5 when we divide by 2. Thus, x is equal to square root 5, or x is equal to negative square root 5. So here we have 2 different x values upon eliminating our y squared. Okay, so we're going to do a little bit of bookkeeping here. And on the left side of this line here, we're going to say x is equal to square root 5 and see what we get when we plug it in. Let's do equation 1 such that x is equal to square root 5. See what happens. If we plug that in, the square root of 5 squared would be 5, plus y squared is equal to 9. Okay, not too bad. Subtract the 5 over, and we get y squared is equal to 4. This then implies that y is equal to either 2 or y is equal to negative 2. So notice here, when x is equal to the square root of 5, we have two possible y values. So we can have the point either square root 5, 2, or square root 5, negative 2. These are both solutions when x is equal to the square root of 5. Now let's let x equal negative square root 5. See what happens here. Again, we plug it into equation 1. We do equation 1 such that x is equal to negative square root 5. And we get negative square root 5 squared. It's going to be 5 plus y squared is equal to 9. Again, subtract over the 5, and we get y squared is equal to 4. Take the square root of both sides again, and we get y is equal to either 2 or y is equal to negative 2. So again, we have two possible y values when x is equal to the negative square root of 5. So we need to account for both of these possibilities. We have negative square root 5, 2, and negative square root 5, negative 2. So in our final answer, we have 4 different coordinates that work. Square root 5, 2, square root 5, negative 2, negative square root 5, 2, negative square root 5, negative 2. We can plug them all in and see that they will actually work in both. Plug in square root of 5 here, you get 5 minus 2 squared is 1, 5 minus 4. Square root 5 here, and plug in a negative 2 here, same idea. If we plug in a negative square root 5 and a 2, and a negative square root 5 and a negative 2, we're going to get 1 as well. We can do it for this one as well. I just don't want to take the time. You can check for yourself if you want to. But the point is, the reason that you want to do bookkeeping here is you want to make sure you know which x values are matching up with which y values. Because sometimes it gets a little bit confusing. Try one on the accompanying worksheet. Solve the system with elimination. 3x squared minus y squared is equal to 11. X squared plus 4y squared is equal to 8. The next topic I want to talk about is the graphical method. Now note, the graphical method is identical to the graphical method when we were doing linear systems of equations. Just because it's nonlinear doesn't mean that the method changes. We're still going to graph both equations, and we're going to look for intersection points, because intersection points satisfy each equation. Solve the system. X squared y is equal to 16. X squared plus 4y plus 16 is equal to 0. So how do we solve this one? Well, what we want to do is we want to graph both equations. This equation, graph this equation. Call this equation 1 and this equation 2 like normal. We'll look at equation 1 and solve for y. If we solve for y, we get y is equal to 16 divided by x squared. You might remember what that looks like, but we'll graph it in a second. Equation 2. If we solve for y, we would subtract 16, subtract x squared, and divide by 4. So y is equal to negative 4 minus 1/4 x squared. Let's see what we get here. Remember, what we're looking for are intersection points. So anywhere these two graphs intersect will be a solution to the system. Y equals 16 divided by x squared has the form of something that looks like this. I'm gonna graph it for real in a second, but I just want you to remember sort of what it looks like. I have a curve like this and like this. Right. We need to make sure that we get it correct. So if we plug in 1 for x, we would have 16 for y. So that would be way up here. Let's plug in 2 for x instead. We would have 4. Plug in 4 for x, and we get 1. That will be the same on the other side. Something like this. This one, both of these lines together create the graph y is equal to 16 divided by x squared. Now let's graph this one. This one you should recognize a little bit more. This is just a parabola opening downward and has a negative y-intercept, a negative 4 y-intercept. Let's graph this one. If x is 0, we have a negative 4. 1, 2, 3, 4. As you can see, if we're opening downward, we're not going to intersect any points. But let's go ahead and graph it anyway. If x is equal to 2, we would have negative 4 minus 1. Negative 5. And if x is equal to negative 2, we get the same thing. For parabola, something like this. You can use graph shifting techniques if you want. So this would flip the graph and shrink it by a factor of 4, and then we would shift it down 4 units if you wanted to do it that way. Notice here that we have no intersection points, so there is no solution. Still a possibility. You can still have no solution as a possibility, just like you could still have infinitely many solutions. More often than not, you'll have a finite number of solutions, but we won't know exactly how many until we see the system itself. Do another example so that we have an example with a solution. Solve the system. Y is equal to 4 minus x squared, and y is equal to x squared minus 4. Now this one's a little bit easier. We have two parabolas as our graphs. So we have a possibility of 2 solutions, 1 solution, or 0 solutions. I.e., if we had something that looked like this, or maybe like this, you could have 2 solutions, 1 solution, and if they completely overlap, then you can have infinitely many solutions. Or you can have no solution, where you have something like this. Now in our case, we're going to actually have 2 solutions. Now let's go ahead and graph these. Start by graphing equation 1. And I'm going to graph that one in red. We have a y-intercept of 4, and it's upside down, meaning that it's opening downward. Otherwise, it's the parent graph. We have something that looks like this. And then for equation 2, this is the parent graph, but shifted down 4 units. 1, 2, 3, 4. Y-intercept of negative 4. So we can already see where we're going to have our solutions at negative 2, 0 and at 2, 0. And we can check to make sure that they are in fact solutions by plugging them into both equations. Plug in 2, you get 4 minus 4, which is 0. Plug in 2, you get 4 minus 4, which is 0. Same idea if you plug in negative 2, because we have a square. Try one on the accompanying worksheet. Solve the system using graphing. Your system is x minus y is equal to 4, and xy is equal to 12. There's not really much else to say about this section. We're really just going over the exact same methods that we went over in the linear systems of equations. but we're doing it with nonlinear equations now. That's going to be it for today. I will see you all in the next lecture.